Okay. Yeah, you start. Thank you.
Okay, good. So thank you very much for the introduction and also for invitation to the seminar. So I'll tell you a bit about a collection of results that we have been developing for the past few years on this problem, as Jali mentioned, broadly of quantum simulation of many-body physics, in particular thinking about how how errors impact, so both the accuracy of quantum simulators and how we can think of quantum advantage when we think of quantum simulation of many-body physics in the presence of errors. I'll try to keep the talk relatively introductory. So if you have any questions at any point, please feel free to interrupt me and ask me for any clarifications or interject with your comments. Okay, so let me begin by perhaps just broadly reviewing the status of quantum technologies, which many of you might know much better than I. And so in order to maybe contextualize what we will be discussing on the more theory side of this talk. So overall, what we have right now are we've already seen several generations of quantum devices that have been developed over the past 2 decades or so very rapidly by our experimental colleagues. So if you go back in early 2000s, we were essentially working with mostly analog quantum simulators, typically in ultra-cold atoms and optical lattices, or maybe some experiments in trapped ions and so on. And in all of these quantum simulators, you essentially had not very well controlled devices. So you could not really do a very precise computation, but you could configure some Hamiltonians on these models, which perhaps you expected to be hard on classical computers, and observe some phase transitions in experiments. And in order to explain those phase transitions, you needed to have a very good understanding of these models using classical methods. And so a lot of experiments in early 2000s were of this form, where essentially the simulators were better controlled physics experiments, but not really something that you would label as a computational machine. So the last few years or so, of course, these devices have been massively improved. They have become digital as well. So you could run analog simulation experiments on them, or you could do digital computations. The noise in these devices has gone down significantly just because of hardware improvement. So we are well below 1% in most platforms. And the noise models are also relatively well calibrated. So you can go and apply learning tools that have also been developed in the theory community to many of these experiments, and you're able to understand precisely the model that you're implementing as well as the noise, or at least to a much higher degree of precision than what was available in early 2000s. And in the recent few years, in fact, probably just in the last year and this year, we have already seen from many big groups in the US, in particular, implementing error correction on digital quantum hardware in both trapped ion systems, in both superconducting systems as well as in neutral atoms. And the hope is that with bringing in error correction as a tool, you can go to even lower error rates, maybe 10 to the minus 5, 10 to the minus 6. And then you could have actually a fairly reasonable computational device, maybe not something that reaches the same error rates as classical computers, but something that you can start using for doing computations that you can trust to some extent. And of course, the eventual goal is maybe getting a fault-tolerant quantum computer where essentially doing error correction is so easy that you can prescribe the error rate that you want, and then you can you have enough number of qubits, enough number of operations, and all the technology with it that you can achieve whatever logical error rates, like 10 to the minus 10, minus 20, that you might desire. Whether that will happen or not, one still needs to see. But already in the next few years, we should have access to devices which have reasonably small error rates. Okay, so on the theory side of things, of course, there's been a lot of interest in developing quantum algorithms, and one could say that the activity in the quantum algorithms community, also that includes both physicists and computer scientists, has been confined in two broad ends of the spectrum. So either developing algorithms for near-term devices, things like adiabatic algorithms, which are physics-inspired, or variational algorithms, which are heuristics. And when developing algorithms for near-term devices, the focus has really been on developing algorithms with very low hardware requirements, often at the cost of any theoretical guarantees. So maybe we do not even understand why a particular algorithm works, but it is a heuristic which has very low hardware requirements. You might still want to implement them on the available machines. And of course, there's a lot of theoretical literature on algorithms for fault-tolerant devices, like the Shor's algorithm being the paradigmatic example there, or quantum singular value transformation and QSVT-based algorithms. which come with a lot of provable guarantees. They come with a very good understanding of why these algorithms work and under what circumstances do they work, but they have very, very demanding hardware requirements, especially if you factor in fault tolerance. But maybe in the next few years, one can apply some of these algorithms for on the devices that are available, or develop some algorithms in the intermediate regime. But what is really an important question here is to try to start understanding how hardware errors and precision errors in quantum simulators affect the fidelity of these algorithms, whether they be heuristics that are coming from physics, or they be these provable algorithms that we have rigorous guarantees for. And this question is relevant not only if we do these algorithms on physical devices, but also if we do these algorithms or perform these algorithms on encoded qubits, which have low but not vanishingly small error rates. So this is what I will mostly tell you about, what we have done on this topic and how that connects to problems in physics. So in my talk, I will focus mostly on algorithms for many-body physics, and in particular, I'm really from a more physics background, physics and engineering, not really a theoretical CS background. So a lot of the ideas from my talk will come from physics, a lot of assumptions will come from physics. And so the problems that we are interested in thinking about are many-body problems. And so many-body problems is sort of a catch-all phrase for problems in physics that have a very large number of particles. What very large means depends a bit on who you ask. So maybe for physicists dealing with toy models, it's just 1,000 particles, but for physicists, for maybe some chemists, it's something like an Avogadro number to 10 to the 20, but typically it is something in the range of 100,000 to 10 to the 20. So you have a very large number of particles, and when you have very large number of particles, your Hilbert spaces are extremely large. And these problems arise in low energy physics and condensed matter and quantum optics, as well as many problems in high energy physics can also be reduced can also be viewed as just a mathematical many-body problem, not very different from what you would solve in low energy physics. So trying to make this a little bit more formal, typically a many-body physics problem is specified by a Hamiltonian. That would be the simplest case, but you can also think of open system problems, which I will mention a bit later on in my talk. But typically they are specified by fairly constrained models. So the Hamiltonian that we are thinking about here is not extremely general. It has constraints of being, for instance, geometrically local on some kind of lattice. So the terms in your Hamiltonian can only act on nearest neighbor qubits. It is constrained to be space invariant and time invariant. So it's usually something that has the same interaction at all points in space. So it has translational invariance in many systems. And it is also time invariant. You're not thinking about a quantum circuit in most problems. You just have a Hamiltonian that doesn't change with time. And what you're interested in doing is looking at some state associated with this Hamiltonian, such as the dynamics of this Hamiltonian, or maybe equilibrium or ground state property, and computing certain very specific functions. So you're never really interested in many-body physics. In most cases, computing the full state associated with the Hamiltonian. You don't really care so much about the microscopic state, but what you care about are some simple observables. And some examples of observables that come all the time in many-body physics context are things like local observables. So these are operators that act only on certain regions in space, or certain neighboring sites in space, or some kind of correlation functions, which are product of local observables, some OX, OY, between 2 points in space, or translationally invariant sums of these kind of observables. So you might have a local observable, and you're now adding up local observables at different points in space, and maybe taking an average of all of these observables. So these are the amount of information that we typically want to extract in these problems. It's much smaller than the whole amount of information present in the many-body state. And this would be an important point to keep in mind. And when you try to do quantum simulation of these systems, you can either do it in analog mode. So you can pick up a device in your experimental, so you can pick up an experimental system which implements the Hamiltonian that you want, or you can configure it in some relatively simple fashion to implement the Hamiltonian that you want. And then you allow the system to evolve in time or equilibrate, and then that allows you to access the dynamics or equilibrium of your model that you're after. Or you can use one of these quantum algorithms that I briefly mentioned on the last slide, which might be designed, for instance, to simulate dynamics, or which might be designed to simulate the ground state properties of these models and implement them in quantum circuits on digital simulators. So both of these options are available in actual experiment. Okay, so what I would be concerned with is understanding errors in many of these methods that are available to simulate many-body problems, right? So more formally, when we think about, for instance, a quantum simulation algorithm, you can generally think of it as configuring a Hamiltonian that is acting on your simulator. And this Hamiltonian could be time dependent, for instance, if you're implementing a quantum circuit. And now you add to this Hamiltonian a error term, which is, in the most general case, it includes some system environment interaction. So it is written as a Lindblad that is also sum of some geometrically local terms. So then we assume that the noise that is acting in our system is acting locally. So there's no very large global noise channel, but some local noise channel. And this is acting with a noise rate delta. So a rate per unit time, the noise acts at is given by delta. And in the presence of this noise, if you look at the observable that you were interested in at the end of your quantum simulation, this observable will, of course, not exactly be equal to the observable that you're after. It is not going to be equal to your target observable. However, there will be a deviation between your target observable and your simulated observable, and this deviation can depend on the different parameters in your problem. And the most important parameters to keep track of here are the noise rate, delta, which comes up when you just write down a system environment model for your simulator, the number of qubits that are associated with that are involved in your simulation, as well as some other parameters, which could be things like evolution time or some spectral property of your Hamiltonian that come on a case-by-case basis. And if you try to think about what this observable error looks like in the worst case, well, in the worst case, you can argue, or you can make this completely formal as well if you like, that if I run my simulator for some time at tsim, so this is whatever the simulator runtime that you need to simulate your observable, then this observable error would typically grow as the number of qubits multiplied by the simulator time multiplied by the noise rate. So the observable error, in general, you would expect that for this observable error to be small, you would either need to have a very, very small simulator time, or you'll have to have a noise rate that decreases with the number of qubits. So that's the typical expectation in the worst case. And so what I would be interested in doing in the next few slides is maybe trying to understand more carefully outside of the worst case scenario, if we have some information about the models that we are studying, then can we give better estimates on this observable error? So can we first understand how these observable errors scale, and then try to identify when is it that these observable errors don't scale badly with my system size? So that means that if I take the observable error and look at it as I make the system size become larger and larger, then this observable error does not go to infinity, but remains some constant, and this constant is a constant that decreases with the noise rate. So as I take my noise rate to 0, this goes to 0. So in this fashion, what I want to do is understand, essentially classify, you might say, it won't be a completed story, at least in my talk, but the goal is to classify problems into noise robust, so where your observable errors do not grow with system size, or noise sensitive, where your observable errors may grow with system size. And then you need very, very low noise rate to have some advantage. Okay, I thought there was a question. Okay, and then the second question that I will then talk about a bit is some of our work and thinking about it more from a computer science perspective, and use some tools that computer scientists have developed in other contexts to understand some questions, some notions of quantum advantage for solving many-body problems. Okay, so let me begin with the first part, and the results that I'll tell you here are in collaboration with Vikram Kashyap, who actually is a student right now in Maryland, and he was one of my master's student, a bachelor student back in University of Washington, Adrian Franco Rubio, who was a postdoc at MPQ at the time, and now he is at Complutense, Yorgos Tiliaris, who is now junior group leader here in Munich, and of course Ignacio Sirac, who is a director at MPQ. Okay, so let me begin by first thinking about the simplest possible setting. And the simplest possible setting is when your model that you want to simulate in your many-body problem is just natively available on your simulator. So what this means is that I don't have to go to my simulator and do anything complicated. Essentially, it is the Hamiltonian of the simulator, or the Lindblad of the simulator, that is what I'm trying to simulate, right? And so this would be the simplest setting where you would not have to worry about complicated strategies of taking a many-body problem and mapping it on the simulator, right? And the main takeaway message here is that if we take this kind of, at least in the simplest case where my model is directly available on the simulator, then if I start with a geometrically local model, which is what I typically see in many body problems, and I map it to a geometrically local simulator, then local observables in my many body problem typically end up being noise robust, simply because geometrically local models have a very restrictive set of quasi-locality properties. And local observables can be be noise robust, even if the full state that you monitor of your simulator is extremely sensitive to noise. And the simplest setting in which you can understand this, where it's extremely intuitive and almost obvious, is in the setting of short-time dynamics. So imagine solving the following many-body problem. I gave you a geometrically local Hamiltonian to start with, and you take a local observable in this geometrically local Hamiltonian, and then you evolve this local Hamiltonian for some time t on an input product state, right? So it's the simplest problem that you can imagine. And then in this setting, if you now add some errors on your Hamiltonian, so maybe your Hamiltonian perturbs slightly, or maybe there is even an environment that then introduces some error onto your system, as long as that error is geometrically local, that's an assumption that we make. But if you look at now the state that you have at time t, the fidelity of the noisy state relative to the noiseless state is in fact going to be exponentially small in the number of qubits. And that's because you have an error at every qubit. So if you look at it in terms of state fidelity, that is going to be vanishingly small. On the other hand, if I just look at local observable, then the error in the local observable is independent of the system size. And this follows very, very obviously from just a light cone argument. Because your Hamiltonian is geometrically local, it has a finite velocity associated with it. So if I take a local observable in this Hamiltonian, its support is not going to spread beyond a linear distance of t from the point, from the initial location of the local observable. And consequently, any errors that we make in the Hamiltonian because of noise in the simulator are only going to affect this observable if they are within this light cone. So if you factor in the volume of the light cone into your, even a back of the envelope estimate, you will realize that the error in the observable would scale as the noise rate times not the whole system size, but only the number of sites that are in the space-time volume of the light cone, and that depends only on t. And you can make this completely formal if you use these Lieb-Robinson bounds that have been developed long back by Lieb and Robinson, and also by Hastings and Coma, and you can prove you can upper bound this delta O completely rigorously. Okay, so that's sort of a very simple observation, just illustrating the fact that there is a big difference when we look at, in terms of noise robustness, when we look at local observables versus when we look at the full microscopic state. Okay, now things become a little bit more complicated when you start thinking of equilibrium properties, and there it is a little bit more difficult to prove these statements and also to understand whether you have robustness or not. Here the simplest problem that you can think of is a ground state problem. So just take Hamiltonian ground state, and now consider the Hamiltonian that you want to simulate. Again, is some geometrically local Hamiltonian. So let me try to get a pointer. Can't see my cursor. Okay, sorry, somehow the pointer is not coming up. But anyways, so you have a target Hamiltonian H, which is a geometrically local Hamiltonian whose ground state you want to simulate. And then you have a simulator Hamiltonian, which in addition to this geometrically local Hamiltonian adds a local perturbation to it. So the total Hamiltonian is not the geometrically local Hamiltonian you want to simulate, but it is another geometrically local Hamiltonian when every site, for instance, has a incorrect term added to it. Then, roughly speaking, you should think about two different cases here. And in one case, the story is roughly speaking the same as that of short-time dynamics. And that is the case when your Hamiltonian has an energy gap. So if you consider the problem where the Hamiltonian has a gap that doesn't decrease with system size, so you have your ground state, which is at some energy, then the first excited state is at a significantly larger energy than the ground state, and this energy gap does not vanish as you make your system size larger and larger. Then you can prove that any local observable is going to perturb only by delta if you perturb the Hamiltonian. So the error between local observables and the ground states of perturbed and unperturbed Hamiltonian is again independent of the system size, so it does not accumulate with n, even though the many-body fidelity, just as in the case of dynamics here, would be exponentially bad in the system size. And the reason why maybe gapped Hamiltonian, having a gap in the Hamiltonian is a reasonable assumption is because in physics, people believe that when you have a Hamiltonian that is gapped, then that corresponds to the Hamiltonian being in the interior of a phase. So if I have some kind of complicated phase diagram for my model, so if I am in the interior of the phase, then I would expect my Hamiltonian to be gapped. Okay. And this result really just follows from sort of these old papers by Hastings and Venn on quasi-adiabatic continuation, which were later made mathematically rigorous by Bachmann and Nachtagale. The other case that you would be interested in when thinking about ground state is the case of of critical models. So when the gap of your Hamiltonian actually decreases with system size, and it does not remain constant, right? So in this case, the story is a bit more complicated, and proving a general result here is very difficult. It is also not true in its full generality. But what we can do here is provide some evidence. So what we did in one of our works 2 years ago was, instead of looking at critical models and full generality, we looked at critical models which had, well, in physics language, a quasi-particle spectrum, but formally, it would just be described by Gaussian fermionic models. And in these models, what one could show is that even though the local observables could be unstable at the phase transition point, so when your gap closes, if you looked at translationally invariant sums of local observables, so observables that were constructed by taking one local observable and adding them up at all the sites, then they ended up being stable. But the stability bound on the delta, on the observable perturbation, was not O of delta, as you get in the case of a gapped Hamiltonian, but it is O of delta to a power that is smaller than 1. So it is less stable than that of the gapped Hamiltonian. The dependence of the noise rate is a bit worse, but it is still as stable as you would. It's still stable in the sense that it is independent of the system size. Okay, and so this maybe provided a little bit of evidence that even if you do a quantum simulation, you are at the critical point, then perhaps you could still hope for, in the presence of noise, getting some information about the critical point, even though the many-body state would again be very, very far away from the true state, and even local observables in this case would probably be very far away from the true state. Then another set of results that one can show here, one can also look at Lindblad simulations. So instead of just looking at simulating open-closed systems, one can also think about many-body open system problems, which are of independent interest. So here the model itself that we are trying to simulate describes a system interacting with an environment. So the target model here is, well, in the Markov limit, described by a Lindblad, which is geometrically local. And when you configure it on a simulator, a reasonable noise model is to assume that the Lindblad perturbs by a sum of local terms. So it perturbs by another Lindblad. And then one can ask the same set of questions, which I will just briefly flash through. I don't want to spend so much time. And the story is very much the same as Hamiltonians. So for dynamics, again, one can prove that all local observables are stable just by a light cone argument. And you need to prove Lieb-Robinson bounds that are different for open systems and closed systems. This was done for Markovian case long ago. And then for non-Markov open systems, this was something that we did also 2 years back. In the case of Lindblad, the equivalent of gapped Lindblad is something called rapid mixing Lindblads, which reach their steady state in log n time. And for rapid mixing Lindblad, again, you can prove, and this was by an old work by Toby Cubitt, that any local observable is stable. So the perturbations in local observables are O of delta, not O of n times delta, right? So the same story as that of gapped Hamiltonian. And then for Lindblads that are fast mixing, so critical, so they don't really go to their steady state in log n time, but might take a time n or poly n to go to their steady state. Then again, in general, they're going to be unstable and no general statement can be made. But for Gaussian fermionic Lindblads, which would describe Lindblads that have some sort of quasi-particle structure, one could again prove that translationally invariant local observables would be stable, very much like translationally invariant local observables could be proved to be stable for geometrically local Hamiltonians. So I won't spend so much time on this because it's sort of the same message that one gets from studying the Hamiltonian, but now in a slightly more general setting. Okay, so unless there are any questions, I will then move on to telling you a bit about some relatively more recent work, which is on problem to simulator mappings. So up till this point, what I essentially told you about was a problem where you where you assume that the many-body model that you wanted to solve was natively available on your simulator, and that you didn't have to do anything complicated from going from the many-body problem that you wanted to solve to the simulator that you had available. Of course, in practice, this is not quite the case. In many body problems, the Hamiltonians or the models that you have are much more complicated than the simulator that you have available. So for example, I often have Hamiltonians that are not simply two local. They have, 4 local terms. If you're simulating some lattice gauge theories, the Hamiltonian terms are much more complicated than simple 2 local terms. They could have interactions that are not easily available in your simulator. So your simulator would typically have a fixed 2 local interaction, but maybe the interaction that you want in your Hamiltonian is not available in your simulator. And you might want to simulate open system models. So you might want to simulate Lindblads with complicated jump operator or complicated system environment interactions, which are again not available in your simulator. On the other hand, your simulator would have a fixed two-local interaction. It would have some time-dependent control that it allows you, which maybe makes it universal. So you can do anything you want with it, but you just cannot take your Hamiltonian or your model that you want and directly configure it on the simulator. You might have to use an algorithm, and many times it gives you the possibility of doing intermediate measurements and reset, which can enlarge the capabilities of the simulator in order to, for instance, mimic some kind of open system dynamics. So in order to now take a target problem, which is more complicated, onto the simulator, what you need to do is use what I dub as a problem to simulator mapping. That is essentially, you can think of it as an algorithm that you are implementing on your simulator, but sometimes these algorithms are kind of more analog in nature, right? So they are analog and sometimes they're analog digital. And there are many, many available problem to simulator mappings in literature. They range from things like Trotterization, which is essentially a quantum algorithm that takes a Hamiltonian and converts it into a quantum circuit. Or you could have something a little bit more analog. So like you can do a Floque-Magnus expansion. What that means is that your simulator is time dependent, and you can drive it periodically as a function of time. And then by driving it periodically as a function of time, on average, you implement a effective Hamiltonian that might be different from just the simulator Hamiltonian, or might look different from just the simulator Hamiltonian. And then there are ways in which you can design this systematically that people have worked out. Or you could do something like perturbative expansion, where in your simulator, you put a very, very high an energy penalty on some subspace using a Hamiltonian, and then projected onto the Hamiltonian, you can implement a larger class of Hamiltonians that was just immediately available to you. So all of these mappings would then allow you to significantly expand the set of Hamiltonians that you can simulate on a simulator with just some restricted interactions. Now, if you just believe what I said, you might think that, okay, now what is new? Then you essentially give me a mapping which allows you to take a problem and put it on a simulator. And we have already understood how errors on simulators affect some many-body problems in the previous slide. So why do we have to revisit this problem again? And the reason why we have to revisit this problem again is because problem to simulator mappings are not as simple as I made them sound. They often come with a simulation time overhead. So what that means is that these mappings need to simulate longer in order to be more accurate, right? And to appreciate this, the easiest example to take is Trotterization. So I'm sure many of you are familiar with this. Now imagine that you'd started with a Hamiltonian that you want to simulate. And let's take, in theme with my talk, a geometrically local Hamiltonian. And you implement this geometrically local Hamiltonian by a sequence of some small geometrically local sequence of gates by only evolving according to every term in the Hamiltonian for some short time, epsilon. This mapping Trotterization is going to be accurate only when epsilon goes to 0. And even though epsilon is going to 0, so you might think that each of these gates that I'm implementing is not a very long time evolution. It is essentially taking one term in my Hamiltonian and evolving it for a very, very short time. You also have to account for the fact that because this Hamiltonian is not available directly on the simulator, I would implement them typically just by implementing a universal gate set. So what that meant is that for each of these gates, even though they have evolution, they are evolution for time epsilon, the amount of time it would take on the simulator to implement these gates is θ1. So it's some constant which doesn't go to 0 as epsilon goes to 0. So the total simulator time that you have will be t divided by epsilon and not just t. And then, as you all very well know, in order to make the Trotterization accurate, I have to take epsilon to 0. And in fact, if I want to get the many-body state to be accurate, depending on the Trotter formula you use in the order of the Trotter formula, the exact estimate of the epsilon could be different, but it goes down polynomially with n and the evolution time. So the total simulator time always diverges as your epsilon goes to 0. And this is what I call a problem to simulator overhead at the beginning of the slide. And so now when you factor in noise into this simulation, then you might wonder, because the noise is acting on the simulator and the simulator now has to evolve for a very, very long time in order to get your simulation correct, then is it true that in the presence of noise, this might render the problem unstable and there's nothing you can do about it? So the stability conclusions that we derived earlier are only applicable to the case when my problem is mapped directly onto the simulator and not when I go through one of these more complicated mappings. So I will try to answer this question, and we will think only about the simplest case here, which is the case of dynamics. So I take a again, the simplest setting, I take a Hamiltonian, evolve it for a short time t, and then I measure some observable after evolving my Hamiltonian for some time t. And then I have some simulate problem to simulator mapping, which could be Trotterization, as I explained, or one of the other mappings that I did not explain so deeply, but we could plug this in here. And then you would simulate it for some time t sim, which is going to be much, much larger than t. And then you go and measure the same set of observables. And what I would be interested in, as I was doing earlier, is characterizing the error between the target and the simulated model. And this error is going to be a function in general of the noise rate, the system size, and the evolution time. And I want to understand how this function varies with respect to these three parameters. And as I already explained to you, just from Lieb-Robinson bounds, if you didn't have a problem to simulator mapping, so if U-sim was exactly implementing the Hamiltonian, this would scale as delta times t to the d plus 1. Just by a light cone argument, there would be no system size dependent. You can understand this. You can maybe sort of guess whether f is a function of n by also thinking about the simplest case where you're just measuring a single local observable, where you're not measuring more complicated observables, which are sums of local observables, or you're not parallelizing the measurement of many, many local observables, but you're just measuring a single local observable. And then one strategy is to avoid this system size dependence on your simulation, which at least works for this case, maybe doesn't work more generally, is that instead of taking your problem to simulator mapping and then applying it to the Hamiltonian on all the qubits, you first restrict your Hamiltonian to be in the neighborhood of the observable, and then apply problem to simulator mapping on only this restricted Hamiltonian, right? So you can take your observable O, and you can say that, well, in time t, I only would need to be in a O of t distance from this observable. Anything beyond that doesn't really affect my observable very much. So I can take my Hamiltonian, I can restrict it to this distance t around my observable. And when I restrict it to the distance t around my observable, I can put it into my problem to simulator mapping. And then I've removed system size from the picture. In particular, I've replaced system size with t to the d, where d is the dimensionality of your lattice. And then any error that you incur is going to be independent of n because there is no n in your picture. So this maybe already gives you sort of an intuitive guess on why maybe this could hope to work, because you have geometrical locality in your model. Now, of course, in practice, this is not what you would do. In practice, you're not going to customize your simulator to every observable that you want to measure. So in practice, what you would like to do is take the full Hamiltonian, implement it on the simulator on all the qubits simultaneously, and then measure whichever observable that you want. And sometimes you might want to measure multiple observables in parallel. And so then, of course, the argument that I just gave you doesn't work trivially, and you have to worry a little bit about how this problem to simulator mapping comes into picture. Okay, but this is exactly what we did. So in one of our recent work, what we tried to do is analyze this problem rigorously. So we took several problem to simulator mappings that have been developed by other people. So we only did like the point of this paper was to analyze the noise robustness of this problem to simulator mapping and not really develop new problem to simulator mapping. And on the technical side, the idea was to develop or use local remainder expressions for this mapping. So for instance, in the case of Trotterization, these were developed by the work again at Maryland by Yuan Su and Andrew Childs. And for Floque-Magnus expansion, Perturbative expansion, sometimes we have to develop some of these on our own. And then you can combine these remainder expressions for your local observable errors together with Lieb-Robinson bounds to get bounds on this delta O. But those are all technical details. And the final results that one got was that if one actually carefully analyzed the error in local observables for all of these problems to simulator mapping in all of these different cases, so Trotterization, Floque-Magnus expansion, these perturbative expansions, or shiftable transformations, as well as Lindblad simulations. So we also looked at open system simulations. Then the observable error were always independent of n. That is the first point to make. They depended as a power of t, and they depended as a power of the noise rate. The powers that you get here, especially on the noise rate, would depend on the specifics of the problem to simulator mapping. So for instance, they could depend on the order of the Trotter formula, the order of the Floque-Magnus expansion, and so on. And they would depend on the dimensionality of your lattice, but otherwise there would be no other system size dependent in your system. And so what this really told you was, even when you account for the simulation time overhead, then increasing the number of qubits doesn't really change the picture compared to what I told you about in the absence of problem to simulator mapping, and you still retain these observable errors to be robust in the sense that we defined earlier. Okay. Okay, so with this side, now we'll move on to the next part on the question of quantum advantage. Maybe I can pause a bit if there are any questions. I can answer them, or Okay. Okay, so there are no questions. Let me continue. So, so the next thing that I will now try to do is, having told you a bit about how we looked at the effect of noise on quantum simulation of many-body physics, to also try to understand the question of quantum advantage in many-body physics, right? And I'm going to begin by telling you a relatively simple thing. It's almost obvious for many of you, and that's like the statement also is obvious, is that decreasing error allows for longer computation. It's a very, very simple statement. What do I mean by that? So to appreciate what the statement is, make it slightly more precise, but not much more precise than what is written in the title, is to consider the following situation where I have n qubits. I perform some unitary circuit with g gates, and imagine each of these gates fail with a noise rate delta, right? So with probability delta, these gates are wrong. Then if I look at the error in the observable that I get at the output of the circuit, then in the worst case, I will get an error that goes as the number of gates times delta. So the total number of gates that I'm applying multiplied by the probability of failure of each gate, that is an upper bound on the total observable error that you make. What this means is, another way of interpreting that is that if you say that I want to attain a particular error, so for instance 10 to the minus 3, then the number of gates that you need to apply has to decrease, is increased as your noise rate decreases, right? So if my number of gates will be upper bounded by this 10 to the minus 3 divided by delta. So if I make my delta smaller and smaller, I can do larger and larger number of gates. And so what that means is that as noise rate decreases, you have available more circuit depths to do more computation. And in terms of classical computational complexity, what this means is that the class of problems that you can solve up to a certain precision, in the presence of a certain amount of noise, to solve the same class of problems with classical computers while having the same precision, which is 10 to the minus 3 in this case, the computational time required by the classical algorithm should grow exponentially with 1 over delta, right? So generally speaking, as I make my noise rate larger, there will be sort of the classical algorithms will lose or are expected to lose in compared to quantum algorithms for simulating at least generic quantum problems. And this, of course, is something that if you read papers that have tried to develop algorithms to simulate noisy circuits classically, we also have written some of these papers, and all the results always have an exponential scaling with 1 over noise rates, even though they may be polynomial with system size, but always with noise rates, there is an exponential scaling. And it is more or less because of this very simple fact that lower noise rates allow you for larger computations. Okay, so now I want to understand the same set of questions for many-body problems. And here there are a few subtleties that we have to keep in mind. And I will introduce some of these subtleties in a bit. So the first subtlety is that many-body problems are a lot more restricted. So as I mentioned, they're space-time invariant often. And often you're interested in thermodynamic limits. That's why we were making a fuss of taking n to infinity in the previous section of my talk. So for example, a particular kind of many-body problem that is very, very common in physics, also has been studied in the CS literature, is the ground state energy density problem. So what is the problem? So I give you a Hamiltonian, which is translationally invariant. So the Hamiltonian is formed by geometrically local terms, where each term is the same on n qubits. And then you have the ground state of this Hamiltonian, and then you try to compute the energy density of this Hamiltonian in the ground state. So you try to compute the expected value of h on the ground state, and you take the average of this expected value to the number of particles, right? So for this energy density, what you can prove by a relatively simple argument is that as you take the number of particles to infinity, this number converges. So this has a well-defined thermodynamic limit, no matter what Hamiltonian you put in, as long as the Hamiltonian is geometrically local, right? So in a many-body physics problem, what you would be after is computing this E, which is the limit of n going to infinity of your energy density observable, and not necessarily after computing h for a certain system size. You might want to analyze h for a certain system size as a means to compute E, but the final computational problem is to compute E. So one subtlety here, which for computer scientists is relatively obvious, but maybe in physics we don't think about it this way, is that there is no system size parameter in this computational problem. So I defined the problem of computing an energy density, which is a limit n to infinity of the ground state of a Hamiltonian. So the n has been removed by definition in some sense from this problem. But what that tells you is that you need to measure the computational complexity with respect to some other parameter. And the other parameter that is relevant here is the precision. So because E is, of course, a real number, so you cannot compute it perfectly on a quantum or a classical computer. You can only compute it to certain digits of precision. And then that is the precision parameter is the parameter that you would need to vary and understand how your algorithm, classical or quantum, scale. So for instance, you could choose to declare quantum advantage in a many-body physics task, not in the traditional sense. That would not be very meaningful if you're looking at problems at a thermodynamic limit, where you're looking at the computational complexity taken as a function of system size. But you can declare quantum advantage with respect to precision. So you could say that if my quantum algorithm takes time that goes polynomially in 1 by epsilon, but a classical algorithm takes time that goes as exponentially with 1 by epsilon, then my quantum algorithm has, or my quantum simulator has a quantum advantage in the ground state energy density problem. And the other perspective, as I showed you on the last slide, that decreasing noise rate results in allowing you to do larger and longer computation, and that means that my classical algorithm will take exponential time to keep up with the computations that my quantum algorithms can perform. So there you can also introduce a similar notion, and you can ask that notion here, and that is that we can say that a set of problems has quantum advantage with noise rate scaling if, when I introduce noise in my quantum simulator, I can use the quantum simulator to attain a precision that decreases with delta. So it is delta to some power. And of course, it cannot achieve precision 0 in the presence of noise, because your noise is there and that's going to affect your simulator in some way. So you cannot expect to have precision 0, but you can hope to get a precision that decreases as you make your noise rate smaller and smaller by whatever means are available to you. And it reaches this precision in time that goes polynomial in 1 over epsilon, which is the same thing in the setting as polynomial in 1 by delta, whereas a classical algorithm takes time exponential in 1 by delta to attain this precision. And what would be very interesting from a physics standpoint is to be able to make these statements for the same problem. So in the previous slide, when I talked about quantum circuits, what I just said was that you can have deeper quantum circuits if you make noise rate smaller. So, but by the fact that you going to deeper and deeper quantum circuit, you were changing the computational problem of simulating completely different quantum circuits. Here, what I want to do is keep the same Hamiltonian, so a Hamiltonian that is fixed. I simulate it on my quantum simulator to a precision that is set by the noise rate in your system, or in the noiseless case, I simulate it to some precision. And then as I decrease my precision in my system, either by reducing the noise rate in the noisy setting or just by reducing the precision in, as an input to your problem, then without changing the problem, a classical algorithm takes longer and longer time to keep up. So I want to keep the problem fixed and then study how these computational complexities change as I make my epsilon go to 0 or delta go to 0.
Rahul, can I ask you a question?
Yeah.
So this noise here, that's the noise of your classical or your quantum computer?
The quantum. So we are always assuming that the classical computer can do things perfectly. And what we are assuming here is that the quantum simulator in the presence of noise gets some limited precision, which is delta to some power alpha. And then I ask my classical computer to get the same precision as my quantum computer.
But so how is that different than from... Oh, I see. Okay. So it's sort of, yeah, okay. It's similar to the first point.
Yeah, it's related. They're very related. Yeah. So, I mean, it's just renormalizing the precision in terms of delta.
Right. So I was going to complain that, oh, I mean, why are you putting delta to be the noise of the classical computer, but you're assuming classical is perfect. Okay,
yeah. Okay. Good. Okay, so let me give you sort of the status of the ground state energy, or generally translationally invariant problem as studied by computer scientists. So as I said, I'm not a computer scientist, so my picture is very, very cartoonish. So for me, there are like 3 main things: whether things are classically easy, they are quantumly easy, classically hard, or they're quantumly easy quantumly hard and classical hard. There are different complexity assumptions that might come into play. You might want to use BQP not equal to BPP, or NP not being in BQP, or you might want to have some more nuanced complexity assumption that are related to log space computations and QMAX and BX class. And so there are a lot of technical details on how one establishes whether something is quantumly and classically hard. And computer scientists sometimes would put some of these complexity assumptions on more firmer grounds than others. this, but let's say for now, we don't worry about these details and just try to understand what is known. Okay, so in the classically easy many-body problems, there are essentially quite a lot of work in many-body community in order to cook up models where you can simulate things on classical computers or even analytically, and this is sort of a very useful exercise in just understanding physics. And in some cases, this has been sort of crowning achievement of classical algorithms for many-body physics. So for instance, one big result that probably all of you know about is 1D gapped Hamiltonians. And 1D gapped Hamiltonians, there is a provable classical algorithm to get to the ground state, and in fact, even get the whole ground state as MPS and including the observables, right? For simple models like stabilizer Hamiltonians, you can often use, simple ideas from Gottesman-Knil theorem in order to simulate a lot of their ground state properties. And then if you go to other integrable models like Gaussian fermion models that I also mentioned, or some models that have some other form of integrability like beta integrability, you can often cook up other methods of computing the ground state property. So there are these class of models that are classically easy and quantumly easy and are many-body models, right? Now, what we also understand is that that these problems are quantumly, that there are, in the worst case, the ground state energy density problem is in fact even hard for quantum computers, even if you restrict yourself to translationally invariant models. And this was first proved by Gottesman in a setting where the Hamiltonian had to be changed with the precision. So in Gottesman's oldest paper, he had to take a different Hamiltonian for every precision that you were inquiring your energy density to. But in a recent paper by Dorrit in 2 to 3 years ago, she fixed this issue and she proved that you can have a single Hamiltonian term. And then as you reduce your precision, if you were able to solve the ground state energy density problem to smaller and smaller precision, you would in fact be proving that QMAX is equal to PX. And that again is something that, QMAX is equal to NPX. And that is something that people don't expect to be plausible. And so that showed that you cannot actually expect to solve these problems on quantum computers. And therefore, they would probably be hard for classical computers. And what we want to understand is, are there any instances of translationally invariant problem that sort of fall in this middle, which are quantumly easy but classically hard? And at least from physics perspective, this is where most of the physical problems should sit. We do not really expect problems in physics to be sort of these worst case quantumly hard problem, even though you can often disguise these worst case quantumly hard problem to look very innocuously like problems in physics being completely translationally invariant, geometrically local, and so on. But one would expect by maybe, this is sort of a belief by Church-Turing thesis that your quantum physics problems are simulable on quantum computers, but not on classical computers. Maybe they're hard. So we wanted to make more precise what this intersection really meant.
Hey, Rahul, I have a question.
Yeah.
Why would you expect that for ground state energy problems to have, quantum easy and classically hard things? Like for evolution, it's obvious, but for ground state, actually, I don't know, it's not so obvious.
Well, if you have like a 1 over Paulian gap and connected adiabatic paths.
Okay.
So I mean, then that would be like quantumly easy and classically hard. Yeah. So I think I would say that, whether or not this is true for a specific model, I'm not claiming anything. So what I would like to do here is provide some argument that there are at least some problems where we have some belief that they are quantumly easy and classically hard, and they are translationally invariant and so on. Yeah. Mm-hmm. Okay, and so this is for the Hamiltonian ground state energy density problem. And of course, you can ask this question for a much richer class of models that do exist that the people, physicists study all the time. So open systems with, for instance, in open systems, you can study instead of ground states, you can study the fixed points, and you can ask the very, very, very same question. So computing local observables or, energy densities in the fixed point of Lindblad's. And then as far as I know, there is sort of no systematic study of where these other problems other than the ground state problem kind of lie. Are they, classically easy, quantumly easy, both or none, and so on and so forth. So that's another question that more or less remains not so well understood. Okay, so what we did here was to, first of all, identify that if we want to look at something that is quantumly easy and classically hard, then it's sort of a BQP style problem because it is going to be solvable by a quantum computer. So it should be in BQP, but it is not a classically easy problem. So it is probably something that is not in P or BPP, but in BQP. And the only way of proving a complexity theoretic hardness would be to try to encode a BQP hard computation or a BQP complete computation into one of these many body models. Now, the issue that you immediately face here is the fact that you have have translational invariance, and so would not be possible because the number of parameters that you have in a translationally invariant model are significantly smaller, exponentially smaller in some sense than the number of parameters that you have in a general translationally varying problem. So if you try to encode a full, a translationally varying circuit into a translationally invariant problem, so a BQP hard problem into a translationally invariant problem, then you will not be able to succeed because of a parameter counting argument. So what this meant to us was that, well, we have to change our assumption a little bit, and instead of starting off with the assumption that it is hard to simulate all possible translationally varying quantum circuits, what you can do is you can instead start off with a weaker assumption, but which is also something people do see in practice, is that it is hard to simulate translationally invariant quantum circuits. So what I do is that I start with the following problem where I start with all the qubits in a product state, which are all the same. I start with a single quantum circuit where all the gates are all the same as well. And then I evolve under some depth, and you can actually imagine that this is happening on an infinite lattice, doesn't really matter. And I apply a certain depth, and then I measure an observable. And then I'm going to assume that computing the expected value of this observable to a precision that goes polynomially is 1 over depth is going to take exponential 1 over depth classical time. And this you can convince yourself that you don't have sort of a trivial algorithm where I just keep track of the qubits in the light cone of your observable and beat this sort of complexity assumption. So at least no trivial sort of solution exists for this complexity assumption. On a case-by-case basis, maybe you can solve this for certain unitaries, but you don't expect there to be some general purpose algorithm that solves this problem. Now, you might be thinking that, am I not solving my problem by assumption? Well, no, because I'm making a hardness assumption and dynamics, and I still have work to do in order to show that the ground state energy density problem, as well as other fixed point problems in Lindblad's that I have, are going to be at least as hard as simulating these quantum circuits. Anyway, so that's what we did. So what we were able to show was that you can have instances of ground state energy density problems which can be solved on a quantum computer. So you could prove that they have sort of 1 over poly n gaps, or polynomially for a finite system size 1 over poly n gaps. So you can reach them, and those gaps, and you have adiabatic paths on quantum simulators that you can use to get to this ground state. And if you could simulate all of these problems on a classical computer, you would end up simulating these translationally invariant quantum circuits, which at least I'm positing is unreasonable. So they fall into the
question.
Yeah.
So it's x to the d, right? Not 1 over d.
Yes, sorry, x to the d. Yes, that's a typo.
Right.
Thank you. Yeah. So we could also show here is that if you could simulate, in fact, these local the ground state energy density in some of these encoded Hamiltonians, then you would be able to simulate any of these translationally invariant quantum circuit. Yeah. And so the technical tools here were motivated from the work by Dorrit, and we used these ideas from using circuit to Hamiltonian encodings in 1D and then combining them with a tiling problem. And what this essentially allowed us to do was, in the digits of the ground state energy density, encode solutions to this dynamics problem for different depths. So as you solve the ground state energy density problem to higher and higher precision, you were basically simulating the quantum circuit to higher and higher depths. Okay, and then the same set of problems could be made with respect to noise rate scaling. So one could also show that if you have a noise rate in some of these problems, then you could always tune your simulator to get a error which is O of delta to the power alpha, so it doesn't grow with system size. And then you could show that a classical algorithm will take exponential in 1 over the noise rate to reach the same precision as your noisy quantum simulator. And finally, a lot of the things that we did was also extend sort of these results beyond the ground state energy density problem. So develop a lot of tools like circuit to Hamiltonian encodings or tilings for dissipative systems. So instead of just taking a circuit and trying to encode it into a Hamiltonian, one could do some more work and encode circuits into Lindblad's, and also encode the Robinson tiling patterns into Lindblad's, and then use these kind of tools in order to show that similar quantum advantage statement hold for the Lindblad for the open system problem. But the main sort of intuition here was that we have to pin these complexity assumptions on we have to pin these statements about complexity of translationally invariant models on a slightly different complexity assumption just because of parameter counting that is available to you. Okay, so I think I am almost out of time. So what I'm going to do next is just very quickly flash another result that we put out recently. Some of you might have seen. And the motivation for this result was to answer now the following question, which was kind of bring together the last two parts of my talk, which was about robustness and which was about quantum advantage, and ask if robust many-body problems can have quantum advantage. And that would be ideal because it would tell you that there are problems that are not so badly affected by noise, which are also classically hard to simulate. And so that would put on rigorous footing the expectation that we can get quantum advantage even without having, noiseless or fully fault-tolerant quantum computer. Now, the issue, of course, with this is that all the robust problems that we found, which we can prove that there is robustness, of course, one can conjecture robustness in many cases. And even in these sort of cases, the proofs of robustness are somewhat conjectural because they make some assumptions that are not easy to check. But one underlying theme in all of these models is that you always had states that had exponentially decaying correlation functions. And almost always there was an alternative classical algorithm that could simulate these robust problems, right? So if you took short-time dynamics, it's clear that you can simulate local observables classically. Also, in the case of gapped Hamiltonians, at least in 1D, there are provable algorithms that can simulate them classically. For rapid mixing Lindblads in any dimension, you can simulate them classically. And for Gaussian Lindblads, of course, it's Gaussian, you can simulate them classically. And all of these are classically easy to simulate. So you might have guessed that robust many-body problems are just classically easy. So that would be sort of the guess that you would form. And then what we wanted to do was maybe understand if this is truly the case, or is it just because the problems that we can prove robustness end up being classically easy? So can we expand sort of the class of robust problems? And now if you think of it at a very high level, you would sort of see that if I forget about the fact that the many-body problems that I see in physics are translationally invariant, time independent, et cetera, I would imagine that one particular robust many-body problem, just something that doesn't exist yet, is a fault-tolerant quantum computer. That is, in fact, a robust many-body problem in the strict sense. It's also universal, so anything that you can do with a fault noiseless computer, you can do with a fault-tolerant quantum computer. So this is sort of a example. You would have quantum advantage in solving, simulating a fault-tolerant quantum computer as a quantum computer. Not that you would want to do this, but this would indeed be possible. However, this is, of course, not quite satisfactory because it is very space and time dependent. You have to do syndrome measurements. You have to go and correct your errors with syndrome. Then your gates are fault-tolerant gadget, and all of that becomes very spatially inhomogeneous. And there's no such notion of thermodynamic limits associated with sort of these quantum computers, right? Fault-tolerant quantum computers. And what we would like is really something which is robust, and it has all of these physical properties. So thermodynamic limits, it is translationally invariant, time independent, and so on. Everything is true. And we don't know how to do that yet, but one intermediate step that we think we have done in the recent few months is to be able to use a completely translationally invariant and time-independent system to do fault-tolerant quantum computation. So this kind of constitutes developing a fault-tolerant quantum cellular automata, for those of you who know what this technical term means, right? And so the idea here is that you can take any quantum circuit, you can find an input state that is translationally variant. The input state depends on the quantum circuit that you want to perform. But apart from that, there is just a single gate that is applied at all positions and at all times. And this can perform a single channel, not a gate. It's a channel applied at all positions and all time. And this can perform universal computations. And so this is, I will just flash this result. This was a preprint just 2 weeks ago. And I guess both we and the experts are really trying to make sure that it is all correct. But so I encourage you all to go and also look at it if you're interested. And so the main sort of selling point here is that there is a time-independent translationally invariant channel automaton which can perform fault-tolerant quantum computation in 2D. And the idea behind that is to combine classical error correction with Toombs rule with sort of fault-tolerant concatenated codes implemented in just one dimension. It was known long back. And the initial state of this automaton is a program. This can be prepared with a polylog and geometrically local circuit. And this also furnishes, as a corollary, a quantum memory with completely translationally invariant rule that can keep a single qubit for exponentially long time. So I would just wanted to mention it, but not really. I will not spend so much time describing this in detail. So if you're interested, please feel free to check out the archive and send us any feedback. So yeah, so I think with that, I was just going to thank my students who have done quite a lot of the work that I've presented. So it's at MPQ. I have a group which is titled Theory of Open Systems, and also my collaborators, Yorgos Tiliaris and Ignacio Sirac. With a summary, I'm happy to answer any questions.
Hi, yeah, really thanks for this wonderful talk. Sorry, we were running a little bit short of time. So maybe I have like one more question from anyone.
I can ask.
Oh, yeah, go ahead.
So you have this assumption. I don't. Can you mute actually the? Can you still mute the room? Echoing. Yeah. So this assumption that you have a like if it's all the same unitary, right? The circuit made up of the same unitary and it's still hard at the end. Do you have any ideas for how to prove it? Because it's kind of a very seems like a non-standard assumption. I guess
Yeah.
you might as well, you know, I mean, I could joke that you might as well just assume the thing you're trying to prove is hard.
Yeah,
Instead
that's
of,
a fair criticism. Yeah, I don't have any ideas on how to prove it. This is a question for the computer scientist, but yeah, that's a fair criticism. Yeah. I mean, I guess it was coming a bit from like sort of the comment that you made, you know, like for dynamics, maybe people believe a bit more that it is harder to simulate
right.
as a function of depth, and you want to connect it to the Hamiltonian ground state energy
Yeah,
density.
no, I was saying the opposite. For dynamics, I would expect that I would understand why it's quantumly easy.
Yeah, but we show that it's quantum easy and classically hard. So I guess for classical hardness, maybe for dynamics, you have better. Yeah, but it's a good question. I mean, I don't know how you would approach this problem. It's maybe probably for like the hardcore computer scientists, maybe to have some ideas there. Yeah.
Cool, thanks.
Okay, maybe I just have one quick follow-up question. I know you have proved Lopez theorem. I wonder whether you have some like real, maybe more concrete numbers, like for maybe do you have you thought maybe for a certain type problem, if you have a certain type of machine with maybe some like error tolerance, then you can compute for some problem with some like precision. Do you have that kind of result?
I mean, we have done some other projects where we have tried to develop some tools in order to put upper bounds on this observable errors with classical algorithms. These upper bounds are provable, numerical upper bounds. I mean, off the top of my head, I mean, the upper bounds are still pretty bad in the sense. So I mean, to be completely honest, like all of these arguments that are a little bit more theoretical upper bounds, if you actually plug in numbers, they are not very useful. But even with sort of the theoretical but numerical upper bounds that we got, which was still rigorous via an alternative method, I would still say that, I mean, there's still, I mean, maybe to get 0.1 precision of 0.1, like one digit in noise rates of the rigorous upper bounds would require a noise rate of 10 to the minus 3 or 10 to the minus 4. So I don't know if that's super useful, but that's the best as it goes, at least based on our efforts on providing rigorous upper bounds and observable errors. Yeah.
Okay, yeah, maybe that's something worth exploring.
Yeah, I think it's very interesting to think about numerical tools to compute these upper bounds classically without having to just simulate the whole without having to simulate the whole quantum simulator. So I think that was one thing that we were trying. But yeah, it's a bit difficult, especially for the problem of dynamics, to get something that's useful and reasonable. Yeah.
Yeah, I think just due to the time, so let's thank Rahul again for this wonderful talk. And I since you're removed, but I think you get your work you introduced to Chris, so I think you'll be happy to have people send you questions afterwards. But
Yeah, sounds good.
I'll just conclude here today. Yeah, thanks.
Thank you. Bye. Thanks.